Regularization is probably the most important topic in source estimation that we usually don't talk about. Sometimes you don't find any information about this in papers, but it is potentially something that affects your source estimation and the interpretation quite a lot. Let's just go back to the beginning. So this is the problem we are trying to solve, and I'm still stuck with linear methods here. The forward problem is linear data equals a lead field matrix times the unknown dipole strengths. And what we are trying to do with our linear methods is we want to find some sort of inverse matrix that we multiply to our data to get the unknown dipole strengths. And I mean, this inverse matrix here, the problem is underdetermined, so we have to find some constraints, to get this inverse matrix to get a unique solution. But it's not only going to be affected by the true signal that comes from brain sources here, but also by noise. And what we would like to make sure is that it doesn't amplify the noise, so that ultimately the source estimate here should reliably, or at least approximate what happened in the brain, and it should suppress or at least not be overly distorted by the noise in the data, so the kind of parts in the data that are not due to brain sources. And why is this a problem? So this is just a mini intuitive, hopefully, illustration of what might happen if you invert matrices. So even if you've never thought about linear equations and matrix algebra before, maybe you will get the main idea here. So if we have a relatively simple matrix, diagonal matrix, this would be a simple linear equation where you actually have two independent parameters. So each equation fully determines one parameter, no interaction between them. Then inverting this matrix will simply be equivalent to inverting every individual value on the diagonal, which is not only simple to do, it also produces values here that are within a relatively tractable, reasonable range. So there's nothing that looks particularly dangerous here. If we have some linear dependency between our rows and columns, so now we have some interactions here between our equations, then you see that the resulting inverse matrix will also have off-diagonal elements, and importantly, you now have differences here. So if you multiply this to a data matrix or data vector, then every output here on the other side will be a difference between one value, let's say at one electrode, and the value at another electrode. And differences produce or amplify variance. So we know that different values potentially amplify at least uncorrelated noise. So that is potentially something to be avoided. But here, at least intuitively speaking, these differences look relatively tractable. So we are still in the order of magnitude of the original parameters. But here's a ridiculous example. So imagine you have very highly correlated rows and columns. So here there's only a tiny difference between them. And theoretically, this is an invertible matrix. If we do this in practice, we get these differences now where you have really high values and you compute. And the difference actually in terms of absolute amplitude is tiny. But the difference here between the large positive, large negative value is huge. So if you multiply that to a data vector that also has random noise in it, then you might actually get a result that amplifies the variance due to noise a lot. And you may have completely meaningless parameter estimates. And in the case of our MEG inverse problem, not only do we have highly correlated rows and columns, we actually have a data that is rank deficient because we have more columns than we have rows. So we even have some at least linear combinations of our columns that are perfectly correlated. So we somehow have to deal with that. At a higher level, I mean, what we are trying to avoid is overfitting, basically. So if we don't regularize at all, then we are telling our method, at least if we are using minimum norm estimation and its friends, to explain the data 100%. So you're finding a source distribution across the cortex that explains all of your data up to the last little value with sources inside the brain. And it doesn't matter whether your signals come from the brain or from the eyes, or whether you just put random numbers in, it will find some source distribution that explains those data. but we know that some of our measured activity is not produced by sources in the model. That means not by brain sources. I mean, if it's from artifacts like the eyes or the heart, then we should have applied ICA or something beforehand. But there might still be some more random noise, Gaussian noise, correlated potentially, but still random, still left in the data. And this is what we have to deal with here at this stage of the analysis. The dangerous thing is that this noise may in our source space and it might get amplified. So it wouldn't be a big problem if the noise and the signal have similar amplitudes in signal space and in source space. So if the signal to noise ratio stayed the same, but as I've just tried to explain with my little matrices there, it might actually end up very differently, and we might completely distort our source estimate by amplifying the noise. So if you are familiar with variance amplification statistics or multiple linear regression, it is basically the same issue there. So you have to, if you have highly correlated variables and noise in your data, then you may have to apply appropriate regularization methods. Just a little bit of maths, I mean, to introduce also some of the terms that we then use in our analyses, but it will become a bit more intuitive in a second. So this is the equation. We usually start with lead field times sources equals our data, and then there is some noise that cannot be explained by the sources in our model. That means the brain sources. What we are trying to achieve is we want to find sources that explain our data, and in this case, not to necessarily 100%, but within certain bounds given by our noise measure here. So the difference between the data and the predicted data should be at least equal or smaller than what we expect based on our noise level. Also subject to additional constraints like the minimum norm constraint that should pick the unique solution that has the minimum square of power across sources. We can write this differently. I mean, the details are not important here. By saying we want to give a different weights to the minimization of the norm of our solution, and we introduce this kind of parameter lambda here. And if this lambda was 0, then we would simply say we want to explain our data completely. And the higher this value lambda, the more we are telling our method to not explain our data completely, but leave some variance unexplained, because we think that this might be due to noise. And the higher the lambda, the more variance we leave unexplained. And it's not only the amplitude of the noise that's important, but also its structure. And for that, we assume usually that we can describe the noise, sort of basically what's left here in the epsilon, by a noise covariance matrix, take into account the variance across sensors, but also the covariance among sensors. So we can rewrite everything. And now we still have this lambda here that describes the amount of variance we want to leave unexplained, but we've basically weighted our equations with the noise covariance matrix or an inverse of the noise covariance matrix to make sure we take the structure of the noise into account. And ultimately, this gives us an equation for the minimum norm solution in this case that contains this lambda. That's the regularization parameter. And the noise covariance has to be specified as well. But with a parameter lambda, we usually control how much variance we want to leave unexplained. Okay, now everybody is asking, how do you choose the regularization parameter? And there are a number of methods, but I'm just explaining the one that I'm familiar with based on the M&E Python software. So there will always be some heuristics involved. So you have to make certain assumptions about the, let's say, how noisy your data are. But I'll get back to this in a few slides. But a concept that's important here is whitening. So you can whiten your data. That means you turn them into data with units and orthogonal covariances. So you create new data where all the channels have unit variance and they are not intercorrelated. But the important thing here is that if you do that with all your equations, including the lead field and your data, then you can express all your data as well as the lead field in terms of signal to noise ratios. So by multiplying everything with the inverse of the noise covariance matrix basically means you are dividing everything by the noise level. So you're turning everything into signal to noise ratios. And that means you, first of all, can now put all your different sensor types into one equation, because EEG and gradiometers, magnetometers have different physical dimensions. But once you turn them into signal-to-noise ratios, they are comparable. But also, now you have everything in signal-to-noise ratios, you can choose the regularization parameter lambda, depending on the signal-to-noise ratio of your data. So it has a bit more of an intuitive interpretation. So you can, instead of specifying lambda directly, you can say, I specify it as a signal-to-noise ratio, and then there are certain ways of transforming this into a regularization parameter. So this depends also on the choice of your noise covariance matrix. More about that in a second. And then usually we are still faced with the appropriate choice and of course the appropriate signal-to-noise ratio for our data. And there the problem is, or one of the problems is that signal-to-noise ratio varies over time within one data set. So it will be around 1 for the baseline by definition. It might be large for your P1 peak and an auditory or visually evoked response, and a bit lower before and a bit lower after. It will be different between conditions within your data set, between subjects, and also between participant groups and maybe your patients or your control group. But you don't necessarily want to regularize every time point, every condition separately. That might introduce another confound. And it also would be a bit cumbersome. So usually we are just picking some reasonable value and then we hope for the best. And I hope I can convince you or reassure you later that it's not an unreasonable choice. So usually we choose the value 3, if we are looking at evoked responses, and a value of 1, slightly more conservative here, for raw, continuous, or single trial data. And now let's look at the effect of regularization in practice. So here, first of all, I use the recommended values for evoked responses first. So this would be a signal-to-noise ratio equals to 3. So that would be the default, at least in MNE-Python, for evoked responses. And this is a visually evoked response, a checkerboard presented to the left visual hemifield, which means you expect the right lateralized response here in the inferior occipital cortex. And that's what we see. It's actually quite a nice response here. Focal, some side lobes, bit of spread, but that's to be expected. And here we can also look at the time course of activation of a voxel in the right hemisphere and the left hemisphere. Flat in the baseline, you see the evoked response. So I think that's as good as we can expect it to be. So that's an evoked response that looks like it should look in source space. Also here, look at the scale. I mean, it's arbitrary for now, but we can now compare it to other regularization parameters. Oh, I forgot. So in this case, if I look at the output of the software, it tells me that it explains 64.8% of the variance, but that's across the whole data set, I assume. So not just for this particular peak, but including the baseline. So that's the level of variance we can explain across the whole data set with this regularization parameter. If we now look at the signal-to-noise ratio of 1, recommended for single trial or resting state analysis, I can hardly see a difference here. It looks a bit smoother. So if you are looking at some of the individual peaks, I don't know how well you can see this. Yes, it looks a little bit smoother. But apart from that, at least the topography here hasn't changed dramatically. But look at the scale. So it's less than half now. So we did smooth our data. We are now spending, let's say, less power to explain our data. We leave more unexplained. If we look at the signals in source space, again, smaller scale, but flat baseline, the evoked responses are still there, but the time course has changed as well. So for example, look here. I mean, this peak these peaks are smaller than those peaks. Here they're a little bit larger even. So things have changed. It's subtle, but it's there. And we usually choose this as an R of 1 for the single trial level to be on the safe side. But in order to show what we are really doing with regularization, I mean, let's go crazy. Oh, again, I forgot to mention the variance. So here now we are explaining less variance. So now we are explaining just about 50% of variance across the whole data set. So in order to really illustrate the dangers of overfitting, so I chose a ridiculous signal-to-noise ratio of 300. And in this case, we see a very speckled source estimate here. It's even in both hemispheres across the temporal lobes here. So you just see a little bit here, a little bit there. it's not smooth, and it clearly produces activity where it shouldn't be, so not even close to the true source. And this is in order to explain some of the noise that's in the data that's might not even come from the brain. And if you then look at the time course here in source space, it's completely crazy that there's no evoked response left, really. It's basically just a long baseline interval, maybe with a drift in there. Look at the scale. So now we are basically wasting a lot of power in our source estimate to explain variance in the data that might not even come from the brain. So it's just a very distorted source estimate. And just imagine what would have happened if we hadn't regularized at all, if we had forgotten about it or done something stupid. So it's really important to check how your software package deals with these things. So here we are overfitting, under-smoothing, and this would be a completely meaningless source estimate. So we can then go the other way and under-regularize, if you like. So now I'm using or specifying a signal-to-noise ratio of 0.03. I'm over-smoothing, under-fitting now, and actually, interestingly, it looks quite reasonable. So the peak is still where it should be. It's in the right hemisphere. Yes, you do see also some red, a shade of red here in some parts of the brain where maybe you wouldn't expect it to be, but doesn't look dramatic. The time course and source space, flat baseline, evoke responses, maybe the later responses here have been smoothed out. And look at the scale, very much lower than before. So we've clearly suppressed our amplitudes. But at least the over-smoothing, we may have smoothed a bit more than necessary, but at least the source that we are interested in is still there. But it's not really clear what would have happened if there had been more subtle sources of interest. Maybe nothing as big as the visual evoked response along temporal lobe or something like that. So obviously we may have lost some information. We might just not see it in this particular image here. But at least I think, okay, let's maybe just finish this. So here we explained clearly more variance, 95.2% across the whole data set. I'm pretty sure at the peak, we would have explained mostly 100, almost 100%. So, but now we are explaining most of the variance in our data, even though we shouldn't. And in this case, we are actually only explaining 0.4% of our data. But luckily, within these 0.4% is also some of the interest, some of the activity of interest. So we can call ourselves lucky in this case. But I think what this shows is that within a reasonable range of signal-to-noise ratios, I think regularization is quite robust. And so you can therefore maybe use a reasonable choice of the signal-to-noise ratio and lambda for most applications. But of course, you can't count on it, not necessarily all the time. So what can you do? So just a few things that you should take care of when you're analyzing your data. So first of all, you have to make sure that you've got a good covariance, noise covariance matrix. So a noise covariance matrix is relatively easy to compute, but then you can visualize it to make sure your data actually look all right. So it's another way of visually inspect your data. So here you see the variances for all your sensors along the diagonal and the covariances as off-diagonal elements. The diagonal should usually stick out, so the variance should be higher than the covariances. There might still be a few channels here, also for EEG, that have particularly high or particularly low variance, which may inspire you to go back to the data and check whether some channels might still be worth marking as bad or even excluding. Sometimes you see clusters here of channels that have high covariance. That could be due to different reasons. Maybe these are frontal channels and they pick up eye activity or muscle activity, or who knows, maybe there is still an artifact that you should take care of in one way or the other. But that, at least, if you look at this across your participants, you will probably quickly see what is normal for your data, and then you will potentially find some participants who stick out a little bit. Just another way to explore your data. Also, you can look at the rank of these covariance matrices. So how many independent components are in there that you need to explain the variance in these matrices. So you compute this, for example, for the magnetometers, gradiometers, and EEG separately. In principle, the rank can be as high as the number of sensors, but there might be reasons why the rank is lower. You might have applied ICA, or in the case of EEG, you might have applied average reference. If you use max filter software, I mean, the signal space separation method, this will reduce the rank quite considerably and that is something you may have to deal with in your analysis. So check your tutorials and documentation for that. Also bad channels obviously will reduce the rank, but these are sanity checks for your data to make sure everything's all right. But then in order to check that, and because the rank is usually lower, these matrices are rank deficient, but also for other reasons, you still have to regularize these covariance matrices. I mentioned, I think briefly before, in your analyses, these matrices will be inverted, and matrix inversion usually requires regularization. So you have to regularize covariance matrices before you can use them to regularize your source estimate. And how do you do that? Well, there are apps for that. At least in ME Python software, you can actually check whether they whiten your data properly. So once you've whitened your data, the resulting whitened data should basically have unit variance in the baseline. And the signal should be between more or less plus minus 2. So if you plot your data for the different sensor types, they should be within these red bounds here, within these dashed lines. If you look at the summary here, global field power, then they should be around, these curves should be around 1 for the different sensor types. And in this case, this should be the same for different sensor types. So they are all basically renormalized so that you compare them across sensor types. And if you do that for several methods, different regularization methods for your covariance matrix, in this case for shrunk and empirical, then you can compare how well the whitening worked. And then there are quantitative ways to check which method is best. I mean, there are a handful of methods available. You can run all of them and pick the best one, basically. And this is what they've illustrated here. And I mean, they both look quite good to me, but in this case, the shrunk method turns out to be better than the empirical one. It often turns out like that. I mean, I find, but that's not necessarily always the case. So check this yourself. If you want to read more about this here, the Engelmann and Gramford paper is good for that. So there are ways of doing that, but you should at least check that your covariance matrices are all right and that you've chosen an appropriate regularization for them. So finally, just a few more remarks. I mean, noise estimation is a bit of a dark art, I would say. I mean, because for distributed source methods, baseline activity is not really noise. So if we estimate our noise covariance matrix from the baseline, we are using activity which is mostly coming from the brain. So we are probably overestimating our noise level. And there isn't really that much we can do about it. I mean, except we could use empty room recording, so without anyone inside the MEG, but then we can't do that for EEG. And we may actually underestimate our noise level. So because, well, having a body in the MEG still might produce other sources of noise. So you can't really win here, but I would say better to be on the safe side. So usually, especially if you use EEG, we are using the baseline interval to estimate our noise levels, noise covariance matrices. And the estimation of noise covariance matrix is important, and it will usually need regularization itself. And for that, it's important, well, that you make sure that you're doing it to begin with, visualize the matrix to make sure it looks all right. And ultimately, you can check whether it does what it's supposed to be, what it's supposed to do, namely whitening your data. It's also relevant for beamformers. I mean, beamformers usually need a noise covariance matrix and a data covariance matrix. In both cases, you have to make sure that you are getting those right. It's the details. I'm not going to talk about them right now. And the choice of regularization parameter is important, but it usually follows some heuristics. But the important thing is that it takes into account the noise level of your data and that you know that you are doing it. And ultimately, the proof of the pudding is in the eating. So I would always suggest, once you've done all your data analysis, set everything up, check the plausibility of source estimation results on some simple data. Let's say in the earliest evoked response that you have in the data, P1, auditory, visual, check the sources are where they are supposed to be, because then at least you know that you're not doing it completely wrong. Okay, good luck.